Okay, this is your homework video for lesson 1-4. We are on page 29. And we're starting with number 1. So each term in the following sequence is a rectangular array. So you look at that and you're like, I don't even know what that is. Doesn't matter. You can see the picture. The nth term has n rows and n plus 2 columns. Now you don't have to understand that, but if you look at it, term 1, 1 row. Term 2, 2 rows. Term 3, this is a mistake in the book. It should be 3 rows there. And then n plus 2, if you take a look, if you take n and you add 2, that's 1 plus 2 is 3. So there's 3, do they call them columns? Yeah, columns. Then 2 plus 2 is 4. There's 4 columns. And then 3 plus 2 is 5 columns. So this part is a mistake. This shouldn't be here. Okay, so hopefully that didn't confuse you. Now, the pictures are not necessarily what you're using to do this problem, so you might not even have noticed that that was a mistake there in the book. But you go from 1 row to 2 rows. There should be 3 rows, not 4. Okay, so number 1, letter A, we're going to make a table of values for this expression using these numbers. So the first column is just your n. It's the numbers you're plugging in. 1, 2, 3, 4, 5 is what they ask for. And then next to it, you're just going to put the expression that you're evaluating. And we're just going to go ahead and run those numbers. So inside parentheses first, 1 plus 2 is 3 times n, which again is 1. So that's 3. You can run this all in your calculator. 2 plus 2 is 4 times 2 is 8. 3 plus 2 is 5 times 3 is 15. 4 plus 2 is 6 times 4 is 24, and 5 plus 2 is 7 times the 5 is 35. So that's part A, is just making a table. You might call it a chart. And then part B, we're going to make a scatter plot. That's just a graph. So we got to get used to this vocabulary and not be scared of it. The table is a chart. Scatter plot is a graph. Okay, so we have to graph this stuff. And so normally when we do something like this, if you notice, we're counting by 1, 2, 3, and we want to know what's the value of this. So time always goes on the bottom of our graph, or the amount of something, and then what's going on in this problem will be what's above it. So 1, 2, 3, 4, 5. So as we progress through our terms, we want to see what's going on here on the graph with the value of this expression. So when we pick what we want to count by up here, we need to make sure that the lowest number is included and the highest number is included. Now I'm going to go ahead and start this at 0 on both sides here. And I'm going to count by tens. And that tells me I'll have 35 right in here. So here's 35. And if you want, you can break it up by 5s. And now we should be able to fit everything we need. So at 1, we need to be at 3, so just below the 5. At 2, we got to be at 8, so just below the 10. 3 is 15, right in the middle here. 4 is 24, so pretty close to that 25. Doesn't have to be perfect. And 5 is at 35 up here. Now your first instinct might be to connect those, but this is a scatter plot. All we know is the terms. There's no 1.5 term. There's no 2.6 term. So by connecting it, you're saying that there's values in between these, and there's not. There's just a value at 1 and at 2 and at 3. So we leave it just like that. Okay, number 2. We've got a graph. We're just going to answer some questions. So give the coordinates of P. When you give a coordinates, it's the X and then the Y, and the X is always on the bottom. It's labeled here for you. And so the coordinates of P, the X value is 2, and the Y value is 6. Part B, describe the situation that corresponds to P, giving the term number and the number of toothpicks needed. So that just sounds really wordy and confusing. Basically, and you're going to see this a lot, we want to make sense of the numbers. Cool, we picked the right numbers, but what do they mean? Because in the end, why are you learning all this math? Because one day, whether it's your job or whether it's just everyday life, the numbers represent something, whether it's money, whether it's items, it doesn't matter. Okay, but just having numbers is not good enough. We need to understand the numbers. So 2 represents your term number, and 6 represents the number of toothpicks. So we just want to put that in a sentence basically describing the situation. So you just want to explain those numbers. So term 2 has 6 toothpicks. You're making sense of those numbers, explaining what those numbers mean. In letter C, explain why the domain. Now, domain are your x values. Domain of n is the set of positive integers. Integers are whole numbers. So when you look at the picture, we just described this on number 1. How come we don't connect this? That's basically what it's asking. Integers are whole numbers. How come it's just 1, 2, 3, 4, 5, and it's not anything in between? So we want to explain that. And that's because the term must be positive, first of all, so it talks about positive integers. There's no negative term. And it can't be a decimal or fraction. If you could have decimals or fractions, then we're looking at rational numbers. Okay, but this right here, we're looking at integers because we're only going to have whole numbers. All right, number 3. We're going to make a table and a scatter plot for this using these numbers for n. So basically the same thing we did on number 1, table, scatter plot. So for n, they gave us the specific numbers here. -3, -2, 0, 2, and 3. And it's for the expression 4n minus 5. So we're plugging this in. So when you plug -3 in and multiply, it's going to be a positive times a negative. So we're going to get a negative. So 4 times -3, that's -12, minus 5 is -17. 4 times -2 is -8, minus 5 is -13. 4 times 0 is 0, minus 5 is -5. 2 times 4 is 8, minus 5 is 3, and 3 times 4 is 12, minus 5 is 7. Now, on our first scatter plot, we didn't have any negative numbers. We didn't have to go to the left with negative x values or n values, which we do here. And the value of our expression was always positive, so we didn't go down to the negatives. Well, that's not true here. So we now, when we make this graph, need 4 quadrants, right? So we need to include negatives here. So our n's are going to go from -3, -2, -1, 0, 1, 2, 3. We got to go down to -17. So I'm going 10, 20, -10, -20, +10, +20. Okay, so at -3, we are at -17, so almost down to -20. At -2, it's at -13, so in here. 0, we're at -5. And then we jump all the way to 2. And we're just at +3, so that's going to be just barely up here. And then at 3, we're at 7. Those should line up in a straight line. We're going to talk later about how this is the equation of a line. So this is not going to have a curve or anything like that. This is going to be a nice straight line. Now we don't connect it because like we talked about, okay, these are whole number values. Okay, we're not connecting it, but they do form a straight line. All right, from number 3, we're going to 5. So we're just going to fill in the table based on the graph. So we got -3, 0, 2, and then we're looking for these. And then the value of the expression at 0, 6, -4. So these are your x's. Sometimes it can be confusing which ones you're looking at here. So always find your x. X is right here. So we're talking about when x is -3. What's the value of the expression? That's 4. So value of the expression is kind of like your y value. So we're at -3. So that is at 4. When x is 0, value is -2. When x is 2, value is -6. Okay, now we got to go the other direction. The value is 0, so the y value is 0. That's the up and down. So the y value is at 0 here. So what is the x value left to right? -1. The value is 6, so don't go to 6 over here on this. The value is 6, the y. What's the x? Negative 4. The value is negative 4. Oops, I almost went the wrong way, right? I don't go to x negative 4, I go to y negative 4. The x value at that point is 1. Okay, number 6. Using the graph, what's the value of the expression when x is 2? X is 2. So you're going to go to your x-axis and find 2. What's the value of the expression? It's negative 4. So A is negative 4. How about B? What values of x? So now we're looking for x. Make the value of the expression equal to 2. So don't go to x equals 2. This is y equals 2. We want to know what's the x value. So when I go to y equals 2, here it is. This is the expression. The value of the expression is 2. What is the x value? That's what it's asking you. And that's 5. Okay, over to number 7. Similar question. If x is 5, what's the value? So they just told you x equals 5. Go to your x-axis, find 5. What's the value of the expression? 5. Part B, what value of x? So now we're looking for x. So don't go to the x. You're looking, what is x? When the value of the expression is equal to 5. Value of expression, that's your y. Go to 5. What's the x value when we have this? Now there's 2 dots here. This expression is 5 at 2 different x values. So you have to give both. So at 3 and 5. So when x equals 3 and 5. All right, we did 5 through 7. We're going to 12 through 18. Down here at the bottom. So we're choosing between a set of whole numbers. Okay, those are positive whole numbers. Those do not include negatives. The set of real numbers. Okay, that's all possible numbers. Real numbers is all possible numbers. The set of integers, those are your whole numbers, but it includes 0 and it includes negatives. And then the set of positive real numbers. So those are just your positives, but real numbers means fractions, decimals, all of that. So basically we're looking at positive whole numbers, negative whole numbers and positives, all numbers, fractions and decimals, and then positive fractions and decimals. So number 12, they want you to choose the most reasonable domain. So what makes sense? What kind of numbers would you use to describe whatever's given? So on number 12, the number of people at a restaurant. So first of all, as soon as you're talking about people, we're not going to describe it in fractions and decimals, right? We're talking about whole numbers. And you're not going to have negative number of people at a restaurant. So we need positive and we need whole numbers. And so that would be letter A. 13, the time it takes you to do your homework. Most likely, you don't finish your homework in exactly 20 minutes. Right? There's going to be extra minutes, extra seconds. Okay, so this can be done in a fractional amount of time, but not a negative amount of time. And so real numbers is all your fractions and decimals, but it includes negatives. So the positive real numbers is what we want here, just positives. But we wouldn't say whole numbers because you can finish in a minute and a half or a minute and 45 seconds, right? So it's not just whole numbers. And then 14, the elevation of a place in the United States. This one sometimes can be a little tricky if you're going too fast. So elevation, you could definitely express that as a fraction, right? It's not going to be exactly 2 miles above sea level or 345 feet above sea level. When they talk about elevation, we always compare it to sea level. So fractions and decimals definitely are part of this, but the question is, can you have a negative elevation? And the answer is yes, you can. So you can be below sea level, and maybe it's just not a concept that you've talked about or you're familiar with, so that's okay. But you can be below sea level, which would be expressed as a negative. So if you're right at sea level, that's 0. If you're above sea level, that's a positive. If you are below sea level, that would be a negative elevation. So we need negative numbers, and it's not always going to be a whole number. You could have a fraction. So this answer is letter B. That's the set of all real numbers, positives, negatives, fractions, decimals. All right, on to 15. So we're going to complete these tables. So real quick, let me sketch those tables out. And the other one, same n values. Different expression, similar, but parentheses are different. So we're going to complete the table of values. We're going to go ahead and run the numbers. And then use the table to conclude whether the expressions seem to be equivalent. Well, how do we know? If we get the same answers, we put the same input, we get the same output for both, then they're equivalent. If we get different ones, then they're not equivalent. So let's start with positives, plugging in. 5 minus 3 is 2, times 2 is 4. 2 minus 3 is negative 1, so times 2 is negative 2. 1 minus 3, that's negative 2. Again, use your calculator if you're not good with your negatives. Times this is negative 4. And I'm just going to plug the numbers in here. The important part is being able to compare. And plugging in here, 2 times 5 is 10, minus 3 is 7. 2 times 2 is 4, minus 3 is 1. 1 times 2 is 2, minus 3, that's negative 1. Negative 3 times 2 is negative 6, minus 3 is negative 9, and negative 5 times 2 is negative 10, minus 3 is negative 13. So now answer the question, are these equivalent? No, not equivalent. It is not an equivalent expression, even though they do look similar. Now it does say explain your reasoning. So we're going to say similar inputs produce different outputs. These are your inputs. They get input into the expression, produce this, those are your outputs. So we had the same inputs and we got different outputs. These are not equivalent. 16, find a counterexample to show that this is not true for all real numbers. So you need to pick numbers that makes this untrue. So this statement is saying that these two sides are equal, equivalent. So somehow this does not equal this. Now if you look, both sides look the same except we've got parentheses here. And what do parentheses do? They tell us to do this first. Over here, there are no parentheses. So what are we going to do first? I know we've got n's and x's, but look, there's multiplication and addition. Multiplication would come first. Over here, adding would come first. So think about a situation where that would make a difference. A lot of situations. You can pretty much plug in any number. But let's think about 0, because what happens when you multiply by a 0? So over here, I don't care what n is. Doesn't matter. I'm going to add it to 10. I'm going to get something. If I make x 0, this side will always be 0. It doesn't matter what n is. It's not going to change the fact that this side will be 0. And on this side, if x is 0, I'm going to multiply first and get 0. But then I've got to add it to n. And so if n is any number other than 0, I'm going to get something positive or negative, and it's not going to equal 0. So a good counterexample is when x equals 0 and n equals anything. So just pick a number. I'm going to just use 1. You got to show it. So we've got n plus 10 times x equals n plus 10 times x. Plug in your numbers. So we have 1 plus 10 times 0. And we have 1 plus 10 times 0. Solve each side. Parentheses first here, so that's 11 times 0. Over here, no parentheses, so multiplication first. 10 times 0 is 0, so you have 1 plus 0. Well, multiply this side, that's 0. Add this side, that's 1. These are not equivalent. Okay, that is a counter example showing that this is not true. Okay, 17 and 18. An equation describing a pattern is given. So here's your equation. Equation means equal sign. If you hear me saying expression and equation, if there's an equal sign, that's an equation, equal equation. And then if it's not, and it's just a number sentence, that is an expression. All right, so give 3 instances of the pattern. So that just means plug in 3 different numbers. And then do you think it's true for all real numbers? So basically we're testing this. So anytime you're plugging in numbers as an instance and you're trying to figure out, is this equation true for all real numbers? What you want to do is you want to plug in a positive number, you want to plug in 0, and you want to plug in a negative number, because most positive numbers will produce the same kind of answers. Negative numbers could produce totally different answers. And 0 is always that odd number that messes things up. And so if this is truly going to be a true statement, this has to work for positives, 0, and negatives. So when we pick our 3 instances, we are going to pick those types of numbers. And we're going to make it nice and easy. So first of all, I'm going to go when t equals 0. Let's start with that and see what happens. So we have t minus 2t plus 3t equals 2t. So plugging in 0. So 0 minus 2 times 0 plus 3 times 0 equals 2 times 0. So I'm going to get 0 and 0. So it's 0 minus 0 plus 0, that's 0. 2 times 0 is 0. 0 equals 0, that's true. All right, let's plug in another easy number. Positive, I'm going to go with 1. So t minus 2t plus 3t equals 2t. Plugging in 1. 1 minus 2 times 1 plus 3 times 1 equals 2 times 1. Solve both sides out. So 1, do your multiplication. 2 times 1 is 2, plus 3 times 1 is 3, equals 2 times 1 is 2. So 1 minus 2, it's negative 1. This side's done, so don't do anything with it. It's 2. You can just keep bringing it down. Negative 1 plus 3 is 2. Good to go. Now we need a negative number. I'm going to slide over here. So you got to test your negatives and see, do negatives mess this up? Any negative number is fine. I'm going to just pick an easy one. You can do 1 if you want to. I'm going to do negative 10 because multiplying by 10s is nice and easy. So t minus 2t plus 3t equals 2t. Okay. So I've got negative 10 minus 2 times negative 10 plus 3 times negative 10 equals 2 times negative 10. So minus 2 times negative 10 is negative 20. As soon as I see minus and negative, I can go plus plus. Hopefully you remember that from middle school. Minus and negative is like adding a positive. So really this is just plus 20. Okay, plus 3 times negative 10 is negative 30. That's really like a minus 30. Adding a negative is like minusing 30. And 2 times negative 10 is negative 20. All right, so we have negative 10 plus 20. You can do that in your calculator. That's going to be positive 10 plus negative 30. It's like minus 30. That's negative 20. And we already finished this side. It is negative 20. That comes out equal. This thing's good to go. So to answer the question, do you think this is true for all real numbers? I would say yes. Appears, because you haven't tested every number, there could be something that doesn't work, but it appears to be equivalent. Now, if you just tested positive 1, 2, and 3, you might say it appears to be equivalent, but you really haven't proven anything. You got to test 0 and you got to test the negative. Okay. All right, last one, 18. And for this one, I'm going to, for the sake of time, I'm just going to put the work up. So this is the equation that's given to you. Same thing as we do on 17. You're going to plug in 0, positive, so 1, and a negative. Okay, when you run those, if you run them correctly, they do all come out to be equal. And so therefore, yes, they appear to be equivalent. Same process, a little more complicated just because there's more going on there. But what's important is that you understand to plug in a 0, plug in a 1 or a positive, and plug in a negative. Test them all. If one of them didn't work, then they're not equivalent. But in this case, all of them do.